Let's begin with some conversions here, and then the problems will get more difficult as we go along. So let's go 200 meters per second to kilometers per hour. I would go like this. I'm going to go 200, and I'm going to write meters over 1 second. Same information, just presented differently. 200 meters per 1 second. Now, in mathematics, you can always multiply by 1. Watch, don't write this. If I multiply by 1, nothing has changed. I can do that because you get back the original. Now, what if I did like, I don't know, 3 over the square root of 9? That's legal because it's 3 over 3, which is 1. It's a different looking 1, but it's still 1. How about something like this? Watch. What if I multiplied by 12 inches over 1 foot? That's still 1 because it's a measure over the same measure, right? So this is like 1. You can always multiply by 1. But for this problem, think of where you're trying to go. You're trying to go from seconds to hours. So use some very well-known conversions, for example. How about 60 seconds, 1 minute? 60 seconds, 1 minute, that's the same measure. It's 1. And the benefit of this is because in a moment, seconds and seconds will cancel. In a moment, not yet. And this will cancel seconds, but not minutes, because minutes has to be turned into hours. So along the same strand, let's multiply 60 minutes with 1 hour, because the minutes will cancel with minutes in a moment, and you'd be left with hours, which is what you want. The only thing left to cover is to go from meters to kilometers. So what is the relationship? Well, 1 meter is not that big. It's like just bigger than a yard, a little bit bigger. A kilometer is huge. Like if you ran a kilometer, you're going to get tired. If you run a meter, you've literally taken 1 step. So the relationship here is as follows. 1,000 meters gives us 1 kilometer. And notice that I put the meters in the bottom, so it cancels with meters over here in the top. So now here in a different color, we can do the fun part, which is when seconds cancels with seconds, minutes cancels with minutes, and we have, what else goes away? Meters cancels with meters, so we're left with kilometers per hour, which is what you want. The only thing you have to do on a calculator is go 200 times 60 times 60 times 1 over 1 times 1 times 1 times 1,000. So on a calculator, and the final answer would be 720 kilometers per hour. Final answer. How about 3 grams per square centimeter? And we turn this into kilograms per square meters. All right, so let's see. So we have 3 grams above, and then we have, it says, how you can go square centimeters? I'm gonna write it a little differently. Instead of square centimeters, I'm gonna go centimeter times centimeter. So same thing. And now we want to go from centimeters to square kilometers. So watch this trick. How about we go, well, what's the relationship? 1 meter has how many centimeters within it? So centimeter has the prefix cent, like a penny, which is 100. So the relationship is 100 centimeters produces 1 meter. And I'm actually going to do this twice, because I need 2 cm to knock out the cm in the bottom. And now gram to kilogram, we know that we can go, what is it? It's going to be 1,000 grams to make 1 kilogram. And now the fun part, when things cancel. Centimeter, 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 centimeter. What else? Gram knocks out gram. So we're left with 3 times 100 times 100 times 1, which I don't have to write down, over 1,000. And the units would be kilograms per square meter, right? Because it's meter and meter, that's square meter, which is what you want anyway. So that's perfect. So now what you want to do is turn this into a decimal on your calculator, or whatever number that is, who knows, just some number on a calculator. And those are the units, kilometers per square meters, okay? What about a little bit of scientific notation? So they're like, hey, turn this into scientific notation. So how about 0.0000387? So here's what you want to do. Wherever the decimal is, you want it to be right there, right after the first non-zero value. So how many spaces would you have to slide it over? Look, 1, 2, 3, 4, 5, 6, 7. So the answer is going to be 3 point and then whatever changes left. And it's always times 10. And you just have to decide what goes in the box. I said it was 7, right? 1, 2, 3, 4, 5, 7 spaces was moved. But because you moved the decimal to the right, that would be -7. See that? -7. How about 1 million? What would 1 million look like in scientific notation? Well, a million is 1 and 1, 2, 3, 4, 5, 6 zeros. Right now, originally, the decimal is right there. But you want it to be 1, 2, 3, 4, 5, 6 spaces away. So that would be 1.0 times 10 to the power of +6, because you move the decimal to the left. What about a little bit of physics here? So let's say that there's a car. Right now, the car is going, let's say, 100 meters per second. And then it suddenly decelerates at, let's say, 2 meters per square second for a total time of, let's say, 13 seconds. So there's a car, it's going 100 meters per second, and then boom, it suddenly begins to slow down, right? It's hitting the brakes for 13 seconds at this constant acceleration or deceleration because it's slowing down. The question naturally would be, what is the final velocity, right? What's the final velocity? So to accomplish this, we need a formula. And the formula we can use looks like this. Let's go here in blue. It goes V sub F equals V sub I plus AT, where V sub F is the final velocity, this is the initial velocity, this is acceleration, and this is time. So let's plug in some numbers. So the final velocity, that's the goal. We want to know how fast the car was going after this experiment concludes. We know the initial velocity, don't we? The initial velocity is 100 plus, and then it's decelerating. So instead of 2, I'm going to use -2, right? Because anytime it decelerates, it's a negative acceleration. And then the time is 13 seconds. And that's all you do. And you just go calculator on that, and that'll tell you 100 minus 26. What is it, like 74, I believe? So final answer, that your final velocity would be about 74 meters per square second. And not about, like exactly that final velocity. Okay, so you want to use that formula right there for final velocity versus initial velocity if you're given acceleration and time. All right, now we have 2 examples left. These are the ones that are gonna take up some time. So let's go like this. Let's draw this model. Let's go like this here. Let's go like that there. So let's say there's a car here. And let's say that there's a tree there. And then somewhere toward the end, we're going to start to break. So here's the given. Okay, so the first part of this trip, you are accelerating, and your acceleration is, let's say, 2 meters per square second. And then you're accelerating like this at a constant acceleration for 15 seconds. And let's suppose your initial velocity was 0. The car was resting. You were at a stoplight. Who knows? It was stopped. You accelerate for 15 seconds with this constant acceleration, and then boom, you suddenly look ahead and there's a tree, and you're not trying to hit it. So naturally, you hit the brakes. And let's suppose that from here to there, you apply the brakes. So let's say brakes. So you brake for a total time of, let's say, 7 seconds, and then to reach a final velocity of 0. Right? So you stop. The car comes to a complete stop. The question is, yes or no, do you hit the tree? Right? Do you hit the tree? That's the question. And I think they also have to tell you how far away the tree was initially from where you started. Let's suppose it was 800 meters away. Okay? 800 meters. So Before we do it, let's see. So you're resting, you hit the gas, you're accelerating for 15 seconds, and then boom, you slam on the brakes for 7 seconds. You stop, a complete stop. The question is, did you hit the tree? Yes or no? The tree was originally 800 meters away from you. To accomplish this, we need two equations. One of the equations was the one we just used, actually. Right? Final velocity is initial velocity plus acceleration time. Another equation we need is this. The change in x, the change in the horizontal is equal initial velocity times time plus 1/2 times acceleration times the square of time. So first, we need to know this. We need to know when we're here what the speedometer was saying on the car. You were at rest. You hit the gas for 15 seconds with this acceleration. And let's say we can freeze, like with a remote control, we can freeze the car right there. And then you look down at the speedometer. What is it saying? Before you begin to brake, what does the speedometer read? Let's find out. So to do that, how about we use maybe this first equation there, right? Let's use that first equation for the first part of this trip. So final velocity, we don't know. Initial velocity was 0. The acceleration was 2. And the time was 15. So that's going to give you 30 meters per second. That's a velocity, 30 meters per second. So you know that once you're right here, at that point, you look down, the speedometer says 30 meters per second. If you're in Europe, because here in America, we use, miles per hour, not meters per second. But we know it's 30 meters per second. Let's actually fill that in. Right here, 30 meters per second. Another thing I want to know is this. I want to know how much ground did I cover during that first leg of the trip, right? Let me actually use a different color. Let's use like green. There. How many meters were covered during that time? And that's when this second equation comes into play. You see this symbol, delta x? Delta x means the change in x, like a horizontal displacement, a horizontal change. And that's going to tell us how far it was from where you started the experiment to this marker there. So let's find delta x. So we know this, we know this, we have everything we need to find delta x. Let's find it. So we know initial velocity was 0. The time was 15 seconds. 1/2 is just part of the equation. The acceleration was 2, and the time was 15, and we're going to square that. So go on a calculator, and if you type that in, that is gone. These knock out. That's going to be 225 meters, right? 225 meters from where you rested initially to this marker there. So let me fill that in. 225 meters. Okay, let's see. So like that there. So we know this is 225 meters. Right now, the tree, it's looking pretty safe because it was 800 total. So far, you've traveled 225. You have 575 more meters to go. And you're not going that fast. You're only going 30. You're going 30 meters per second. I put miles per hour because I'm an American, right? So the tree's looking pretty safe. And so we have how much ground left to break? We have 575 meters to go. So now what we have to do is we have to see from this marker going 30 meters per second, braking with all our might for 7 seconds to come to a screeching halt. How much ground, are we talking about there? And we're going to compare that distance to 575, and we're hoping it's smaller than 575 because I'm not trying to, crash into a tree here. Let's go back to this equation there, where our final, and that pertains to this part of the trip. So we know the final velocity is going to be 0. The initial velocity is going to be 30. The time is 7. The acceleration, we're about to find out. So final velocity is going to be 0. Initial velocity was 30. Acceleration is unknown, but the time is 7 seconds. So that'll tell you that the acceleration is negative 30 over 7 meters per square second. So that's the acceleration for the second part of the trip, and it's appropriate that it's negative because you're slowing down, which means negative acceleration. So let me just jot down here that the acceleration is negative 30 over 7. Let's see. So initial velocity is going to be 30. Time is 7, 1/2. Acceleration, ding, ding, we just found it. Time squared is that. Let's see what that is. 105. The heck does that number represent? That's meters. That means that from the moment you started to slam on the brakes, you covered 105 meters. So let's say that here in purple, your car stopped like right there because that little purple strand was 105 more meters beyond the first 225. And if you add those together, it's like 330. So do you hit the tree? No way, not even close. You had way more ground to go before you would hit the tree, right? So for a problem like this, I'd recommend using these two formulas back and forth, back and forth, back and forth. Last example for the day, one that has to do with what we call projectile motion. Let's go to the first quadrant. And let's say that there's a ball here, and it's going to be launched upwards, and it's going to land on the ground over here. And let's suppose that the initial height of the object was 3 meters. All right. And let's say it lands on the ground 9 meters away horizontally. And let's say that it was launched at an angle of 40 degrees. And the initial velocity, V naught, is unknown. So it's a ball, it's a rocket, it's a cannon, who knows, who cares? It's launched 3 meters above the ground at an angle 40 degrees, right, with respect to the horizontal, at an unknown initial velocity, but it lands 9 meters away. For this type of situation, there are two equations you want. One equation that deals with the x coordinate, which looks like this. And a separate equation, let me write that a little bit more to the left. We're going to need some space for the y equation. Y naught plus v naught times time times sine of theta minus 1/2 gt squared. Here we go. So we have two equations, one for the x coordinate, one for the y coordinate. X naught is the initial x coordinate, y naught initial y coordinate of the object, v naught initial velocity, which is the goal, t is time, in this case probably in seconds, sine and cosine are just trig functions, theta is the launch angle, t is time, g is the gravitational constant, which for us in this physics class, g is going to be 9.8 because it's in terms of metrics, meters. We know g is 9.8. We know theta is 40. Let's take g, let's take theta, and let's plug them into these equations, all right? So let me write that down over here somewhere. So this would look like x equals, you know what? We also know x naught is going to be 0, and y naught is going to be 3, because the object is there, and those coordinates are 0, 3, initial x, initial y. So we know quite a few things. So our x equation simplified would look like v naught times time times the cosine of 40. The y equation would look like initial height 3 plus v naught times time times the sine of 40 minus 4.9 t squared. I got 4.9 because if g is 9.8, you can go half of 9.8 to get 4.9, okay? Now, keep in mind what the goal is. The goal is initial velocity. We'll get there. Why don't we do this? Look at this point right there. When the ball, boom, hits the ground, it hits the earth. When it hits the earth, right there at the ground, the coordinates are going to be 9, 0, because it hits the ground, your y coordinate is 0. Let's take 9, let's take 0, and plug them in for x and y. So that'll say 9 equals v naught t cosine 40, plug 0 in for y, 0 equals 3 plus v naught t sine 40 minus 4.9 t squared. Why don't we look at this equation here and why don't we solve for V naught? Check this out. Check out this little trick here. Can you agree with me? Would you agree that if you get V naught alone, that means dividing by T cosine 40 both sides, and that it would say this over here? So now we know what could replace V naught. Replacing V naught could be this fraction because they're equal. And I want to take this fraction, which is V naught, and I want to plug it in right there into this part right there. Let's see what that equation would look like. So it would look like 0 equals 3 plus, and instead of V naught, jot down this fraction, 9 over T cosine 40 times T times sine 40, and then minus 4.9 T squared. Looking at this equation, something really nice happens. This T cancels with this T. So we're left with 0 equals 3 plus 9 sine 40 over cosine 40 minus 4.9 T squared. Why don't we go calculator and type that into a calculator? Make sure your calculator is set to degrees. So this becomes 0 equals 10.55 minus 4.9 T squared. Solve this equation for T. You can add this term to that side, divide, square root, do the math to discover that T is about 1.467. Time equals 1.467. But what does that time represent? That's the time that it takes for the ball to hit the ground, because we plugged in 9 and 0 into this situation. 9 comma 0 is when the ball hits the ground. So the T that you discovered corresponds to this moment in time when the ball hits the ground. So the ball was airborne for 1.467 seconds. How the heck does that help us? That helps us to get the final answer right now, because you can take 1.467, plug it in right there, turn that whole thing into a decimal, and that gives you the initial velocity. So let's go 9 divided by 1.467 times the cosine of 40. So for my problem here, my made-up example, my initial velocity would be about 8 meters per second.